Okay, let's talk about section 5, Cauchy theorem and the integral formula. Okay, so in this section, proposition 2.15, we had a result. If proposition 2.15, so if f from the open disk centered at A with the radius r to C is analytic, and if gamma is a closed rectifiable curve in BAR, then the integral of f along gamma is equal to 0, right? So we know this one. Remember how we proved this? We find antiderivative we find a primitive based on the power series of f. Okay, so we use term by term anti-differentiation to make sure that the series converges and get it. But we know this is if you have a closed rectifiable curve. This case is not always the integral is not always 0. The thing is that we know if we have f of z equal to 1 over z, and we assume this a is equal to 0, then gamma of t is EIT. T is between 0 and 2 pi. It's a closed rectifiable curve, but this integral is 2 pi I. The integral is 2 pi, right? So you can just we already did several computation like this in the wanting number part. So this is not correct for the general case. The reason is that this 1 over z is undefined at z equal to 0, and 0 is enclosed by gamma. So gamma is unit circle and there's a hole. So this point, when we say hole, means this point is not in the domain of f. Why, if there's a hole not in the domain of f, we don't have such stuff? Well, if you want to understand this, you have to go back to the proof of a proposition 2.15. Proposition 2.15 depend on the f of z is equal to 1 over 2 pi I integral along gamma f w minus z dz. And gamma is a circle, and z is inside. This is a gamma, this is a, and this is z, right? We have this representation. And when we try to prove this, I believe this is something like 2.6 stuff. When we try to prove this, we use that phi st. Remember that phi st. Phi st is f of z plus t eis minus z. TEIS minus EIS over EIS minus Z minus f of Z, something like this. You can go back and check it. And this one, this Z plus TEIS minus Z, this is the linear segment connecting Z and EIS, Z and EIS. So you have a Z, point Z, you have a EIS, arbitrary point EIS on the curve, and you connect them. And F should be defined over this segment. And unfortunately for 1 over Z, if you have a Z here, and there is a position like this, EIS, over this segment, the function is undefined at 0. So this definition of a phi st is not well defined. Phi st is not well defined. Okay, so that's why we cannot have a theorem 2.6. Without theorem 2.6, we cannot have a power series expansion. So all the techniques fails. All right, so but you see here, if I just have this circle, but I move this A to any place here, and I draw the circle, a little circle, this like this. Not the circle surrounding 0. I choose A and draw a small circle here. Then you can show that if this is gamma, this little circle is gamma, then the integral of 1 over Z dz over this small gamma is definitely 0 because of the first part. So this gives us a hint. If inside it, the circle there's no hole, then the integral formula, this integral f along gamma should always be 0. Okay, so that's our observation. We're going to show that. Well, but here in this section, we're going to choose a different approach about the similar topic. So in order to approach it, we want to join the Wanding number with our integral formula. We want to get the Wanding number with the integral formula. So first, let's set up our working lemma. So let gamma be a rectifiable curve, and suppose phi is a function defined and continuous on gamma. Okay, for each m greater than or equal to 1, let capital F m of z be the integral of phi w over w minus z to mth power integral along gamma dw. And this is for z not in the trace of gamma. Okay, so the denominator is not 0. This is our definition. We define capital Fm of z like this integral. Then the conclusion is that then each Fm is analytic on their domain. What is the domain? Oh, sorry, not everything not on the trace, so on C without the trace gamma. Okay, it's analytic. Analytic, what is the derivative? And Fm prime is m f m plus 1. It's like a chain. You differentiate first one, you get the second one, and with a proper coefficient m. Okay. So this is the working lemma. We're going to prove this. So first, we show that Fm is continuous. Fm is continuous. Well, let's see. This continuity actually is very close to the continuity of the winding number stuff. But anyway, let's try to see it. So continuity, we just check the difference, right? The difference is the integral gamma phi w minus a to mth power minus phi w minus b mth power dw. Okay, and phi w, let's separate them, and you will have 1 over w minus a to mth power, 1 over w minus b to mth power, and we know it can be factored as a w minus a minus w minus b, and then it will be a very long w minus a m minus 1 w minus a m minus 2 w minus b and w minus a w minus b to power n minus 2 and plus w minus b to power n minus 1 dw, right? Okay, it's this one always correct if a and b are in the domain. The thing is that we fix a. We just talk about the continuity at A, so we fix A in G. Fix A in G in the well, not G, in the domain. We fix a point A, not inside trace gamma. Then choose r greater than 0 with r less than the distance between A and the trace gamma. Well, the trace gamma is compact, so this distance is definitely positive. So we choose a small enough r, just small enough. So you have A, and then you have a gamma here, and you have r. This is r. And then you require b minus a less than 1/2 r. So b should be, this is a, b should be very close to a in the inner disk. Okay, in the inner disk. And the w, what is the w? The gamma. Gamma is, no, not the gamma, sorry, my bad. So the w is on the gamma. So w minus a, the distance will be greater than r, of course greater than 1/2 r. When I present the continuity of an index, I didn't put this 1/2 r because we don't need it. But when we put it in this, when we prove this continuity, for this case, it's better to use this 1/2 r because with this 1/2 r, the rest of the part will be balanced. But anyway, let's see how we get it. Okay, So W minus A is greater than R, is greater than 1/2 R. B is very close to A, so W minus B is greater than 1/2 R. Also, you see here, this is a symmetry we used here. All right, so because the closest point is here, is this point. This point to the exterior part is at least R, 1/2 R. So the W minus A, like this M minus K times ops value W minus B, K, this will be less than 1/1/2 R M minus K 1/2 R and K. It is exactly what? Exactly you flip this 2 for upward, so it's 2 to M, and then you get R to M. All right? So it's bounded by this number. And when A is fixed, we can choose R, and R is fixed. R, remember, R is a fixed quantity. Okay, so this term, each term will be less than 2 to M over R to M. Okay? Everyone. If I do not put 1/2 R, some part will have coefficient 2, some part will not have coefficient 2, and they have different power. It's not easy to write. Okay, so now let's see. FMA minus FMB. We put ops value, and then we're going to put ops value inside the integral. And remember, phi is continuous, so phi, and the gamma is compact, so phi has a maximum value. Phi has the maximum modulus on gamma, because gamma is compact. Okay, so it's less than or equal to integral m phi. M phi is maximum modulus of phi on the gamma, and this part, if you do it, you will have A minus B. A minus B. W minus A times W minus B. It's a 2 R over 2 squared. And the rest of the part, you will have the first one modulus. First one modulus. This is M minus 1. Here I use M. It should be M minus 1 and minus K. So the first modulus is 2 to M minus 1, R to M minus 1. All of them are 2 to M minus 1, R to M minus 1. And modulus of dW. How many terms? We know there are M terms. There are M terms. Okay? There are M terms. And let's move all these steps forward because they are all constant. So you have phi, M phi, A minus B modulus, and you flip it up, you have M 2 to M plus 1 over R to M plus 1, M minus 1 plus 2 M plus 1. And the integral modulus dW along gamma is a total variation of a gamma. Right? So we want it to be less than epsilon. We want this to be less than epsilon. So delta should be epsilon over M phi M 2 to M plus 1 R to M plus 1 and total variation of gamma. Delta is this controls this B minus A modulus. And of course this delta should be less than R, but 1/2 R. Delta should be less than 1/2 R. And delta is less than 1/2 when these two conditions are satisfied, we can get this whole difference is less than epsilon, so function f is continuous. Fm is continuous. Okay, so that's a complete proof. In the textbook, it says details are left to the reader. I want to just present because in the textbook, when they try to prove the continuity of the winding number, the index function, they pass to the 1/2 r. I didn't do that, so I don't want to make you confused. So I tried to do this. It's not difficult. You can reproduce it by yourself. All right. Okay, so we get Fm is always continuous. Fm is always continuous. So what is Fm? So whenever you have a function continuous phi, then this is always continuous. Okay, so keep this in mind. Now fix A in C without trace gamma. And let's call it G, the domain G region. And let Z belong to G, and Z is not equal to A. Okay, we're trying to compute Fm Z minus Fm A over Z minus A. We're trying to compute the limit of the relative ratio. Okay, so it is the integral gamma Okay, let's see, phi w minus z to mth power dz, dw, my bad, dw minus integral gamma phi w minus a to mth power dw, the whole thing over z minus a, whole thing over d minus a. Well, let's check. We can recycle some computation. You see, in this part, I didn't write it completely, but this one is equal to a minus b over w minus a, w minus b. This. All right. So you just get the common denominator is a minus b, w minus a, w minus b. So there is a difference about these two numbers. And when we do this, this is a, this is unfortunate, this is a, this is b. So when you put them into one integral, you actually have exactly the same computation like this place. You only change the variable. And this z minus a cancels z minus a from the numerator. Imagine that. Or if you want, we can rewrite it. But it cancels the numerator part. What you have is just the denominator. Okay. This is -1 and -1. Okay, I just rewrite the this part in terms of z and a, in terms of z and a. All right. So we're going to remember here there are m terms together, altogether there are m terms, So we distribute this one into the parentheses, and I'm going to write a on top. The first one we will have w minus a to power negative 1, denominator w minus z to power m, no minus 1. This is w minus this is m. And dw, this is the first one. And second one, integral phi w. This w minus a, 2. So it's a w minus a to power negative 2, w minus z. Here's minus 2. Here you have one copy, so w minus 1, dw. The last one we will see, this is integral phi w. This is w minus a to power m minus 1, so it's a w minus a to power m, w minus z, dw. Okay, so we distribute this into the bracket, and we consider this one as a function, continuous function, and this one as a continuous function. All the numerator we will consider them as a continuous function. By part 1, by the previous part, we know they are continuous in terms of z. They're continuous in terms of z, right? In terms of z, then we take the limit. Then the limit z approaches a, all these part to certain k. Here the denominator w minus z to power what? The sum is m plus 1. So it should be m minus k plus 1 dw. You check that this is, you see, this is 2. 2 plus m minus 1 is m plus 1. 1 plus m is m plus 1. This is m plus 1. All the terms has the union of the power m plus 1, has a sum of power m plus 1. So here's m plus 1. So this limit, you just use direct substitution. You replace w by a, w m plus 1. This is f m plus 1 of z, a, f m plus 1 of a. Okay? How many terms do you have? Remember, I already mentioned inside the bracket there are m terms. So after multiplication, you have m terms. So fm prime of a, fm prime of a is the limit z approaches a, fm of z minus fm of a over z minus a. It is equal to the limit of each term. They are all fm plus 1 of a, and there are m terms. So we finish the proof. All right, so we finish the proof about the this working lemma. Working lemma will prove it. All right, so actually this working lemma is the application of continuity, and the continuity is very close to the continuity of the Wanning number. So go back to the Wanning number and check it, and then come to the proof of this working lemma. Okay, so now with this working lemma, let's prove the so-called Cauchy's integral formula. The first version. There are several versions. So let G be open subset, be an open subset of the plane. And f from G to C, an analytic function. If gamma is a closed rectifiable curve in G such that the winding number of gamma with respect to W is always 0 for all W in C minus G, exterior part of G. There's no winding number. Then for A in G without gamma, the winding number of gamma with respect to A times f of A is equal to 1 over 2 pi I integral gamma f of G Z minus A dz. Okay, so first of all, let's say before we prove it, let's see the example. 1 over z. 1 over z has a domain G equal to C without 0, right? This is the domain. And the winding number for whatever gamma, for example, is EIT. Gamma t is EIT. Then gamma t W equal to 0. Then the winding number of gamma W is equal to 2 pi I. Winding number is integer, is equal to 1. Already divided by 2 pi is equal to 1. So it's not equal to 0. This equal to 0 case just means we want to remove the hole inside the domain, right? If there's a hole inside domain, then this circle will give us a problem. The winding number is not equal to 0. So this condition removes all holes from the domain. Domain cannot contain a hole inside. Well, this is not contained. It's still outside. It is still outside because your circle cannot, your closed curve cannot include it. Okay, so this is not. Okay, so let's see the proof. The proof, some part is a technical, some part is technical. Okay, so if we have phi from G cross G to C is defined by phi z and W. Phi z and W is equal to fz minus fw over z minus w. Well, if z is not equal to w and phi zz is f prime of z, then we can see that phi is continuous. Phi is continuous, and for each w, fix the w, if each w in G, z to z minus w is analytic. The function, let's not use f, just a function. from z to z minus w. You fix one variable and you just let the other variable change, then that's a analytic function. This is a part of an exercise, but it's just epsilon delta definition. Okay? Okay, so now we're going to have G. G has a property, it has no hole. The winding number of gamma with respect to W is equal to 0. So let's talk about a little bit of topology. So we choose all the W's so that the winding number with respect to it is equal to 0. Not just exterior part, some part of the inside may also satisfy this. Okay, so H is not the complement of G, but the complement of G is contained in H. Okay, the complement of G is contained in H. And this winding number is a continuous function. Integer value. Okay. You have a connected component, then that's always correct. It actually contains like this piece, that piece, several connected components. So H is open. Like for example, your gamma is like this. Then only exterior part. If this is gamma, only exterior part will be H. It's open. And if you have I'm trying to imagine how I sketch it. Okay, I have this counterclockwise. Have this clockwise. Okay, yeah. Now see this part, this point. Remember that I have this counterclockwise. So from here, this point to this point, this is a winding number -1. And when I go in, I get an 8 shape. So this small one is clockwise, so it's -1. So this small region, every point from this small region will give us a winding number equal to 0. So the for this problem, the H is going to be the exterior part plus the interior one. Okay? Yeah. Let me draw it clearly. So I do this one. Yeah. This is what I sketch. I just try to make it bigger. So this is one counterclockwise up to this point, and then when I get in, this becomes clockwise. So H is, this one is clockwise. Yeah, correct. So in this region, the winding number is 0. In this region, the winding number is 1. In this region, the winding number is 2. Because you see, you have one circle counterclockwise, you have a bigger circle second counterclockwise, so the winding number is 2. Exterior part, the winding number is 0. All right. So anyway, H is open. H is a union of this piece and the unbounded piece. And C minus G is H, so H union G is C. It may contain some part inside G. Okay, now let's define G from C to C by G of Z equal to the integral of gamma phi ZW. Phi, this one. Okay. Oh, here C is a union of them, and this part we use F. F is only defined over G. When Z is from G, then we have F, and then we can define this phi. If we don't have, if we have Z from H, then we define this G of Z. G of Z is equal to Fw over W minus Z dW along gamma. So be careful here. F is only defined on G, but this gamma is inside G. Gamma is inside G, so Fw is well defined. Fw is well defined. We just use this quantity and over W minus Z. And Z is inside H. W is still inside G. Okay? Okay, so with this definition, we have to show that on the intersection G and H, the function Gz is well defined, which means those two definitions should match. Okay, so the gamma phi ZW dW along gamma, what's this? This is integral along gamma Fz minus Fw Z minus W dW, right? So this is equal to, we want W minus Z, so we switch them. So it's equal to Fw W minus Z dW and minus integral along gamma Fz W minus Z dW. And remember that we know this is a constant. Fz, this integral is about W. Fz is a constant. We move it forward. So you have integral 1 over W minus Z dW along gamma. That's a winding number. Exactly the winding number. Right, the winding number. And here, remember, this Z belongs to G intersect H. So it is inside H. So winding number is 0. So this term vanishes. So you still have that first one. Okay. So it is a well defined. G is well defined. Okay. G is well defined. Then G is analytic by this lemma, by lemma 5.1. Right? You integrate this one is analytic, this one is also analytic. Analyticity is defined over each part. All right, so G is analytic on C, so G is entire. G is the entire function. G is the entire function. Now let's look at H. H contains an unbounded component. H, remember that H has unbounded component. This is H. Right? It contains unbounded component. So F is bounded F is continuous. F is bounded on gamma. F becomes bounded on gamma, right? And this W minus Z, 1 over W minus Z approaches 0 as what? As Z approaches infinity. And this is uniformly. This is uniformly for W inside the trace of gamma. Well, if you're not so sure about this uniform stuff, you see the distance between Z and the trace of gamma, let's call it capital R. And every point will be greater than capital R. The distance between the W and the Z will be greater than or equal to capital R. This is least distance, right? And then this modulus will be less than or equal to 1 over R. And here, this one does not depend on W, so it's uniform. Uniform, then the limit Z approaches infinity, G of Z is the limit Z approaches infinity, integral along gamma FW, W minus Z dW. This is bounded, this one is uniformly small, so the limit is 0. Alright, so you have G is analytic on C with the limit of G of Z at infinity equal to 0, then G is bounded. G must be a bounded function. Outside the disk is 0, inside disk is compact set, continuous function will be bounded, right? Bounded the entire function by Liouville theorem. By Liouville theorem, we know G is a constant. Okay, G must be a constant function. G is a constant function. We know that G at infinity, constant function will have limit everywhere, the same thing, but the limit is 0, so G is 0. Because the limit at infinity is 0, so G has to be a 0 function. G 0 function, well, let's check one of 0 gamma phi ZW d phi is a gamma Fz minus Fa. Oh, let's put A here. Z minus A d Z. Okay, and if you separate them, you will get the integral gamma Fz, Z minus A, dz, and minus Fa is a constant, move Fa forward. So integral along gamma 1 over Z minus A dz. Okay, and this one is a 1D number. One-D number gamma with respect to A and Fa. And this is exactly what we should prove. Alright, so that's a first version of a Cauchy's integral formula. First version of Cauchy integral. This one is times 2 pi. Times 2 pi. Without this one is integer. It's not does not involve 2 pi. Do I miss some 2 pi someplace? Yes, here. Here I need 2 pi. But it doesn't matter. This one in number is 0, so 2 pi will disappear. Alright, so we finished the proof of the first version of a Cauchy's integral formula. It's very, very, very important. Go back and go through the whole proof and see which part you don't understand, then try to figure it out. Or if you still don't understand, we can discuss. Okay? Thank you very much, and we finish this video.